Hey guys, Unit 5, moles and stoichiometry. Sounds like fun. Stoichiometry. So that is the math of chemistry, dealing with quantities of substances, more specifically products and reactants in chemical reactions. Lesson 1 will be focusing on understanding the mole concept, calculating gram formula mass, and differentiating between formula mass and gram formula mass. And I know you're saying to yourself, what in the world does all of this mean? So we are going to be working on definitions and some math in this lesson to help you. Right now you're going to do a little warm-up on page 2 in your notes. So you'll put today's date, January 2nd, 2014. Hopefully that is the day that you are watching this video lesson. And I want you to take about a minute to look up the definition of a mole. What is a mole and how is it used in chemistry? Not the creature, okay? So I'm going to pause, give you a few seconds to do this, write your answer in the right-hand column, and then we will go forward. Okay, so a mole is a unit of measurement. Abbreviation is MOL, mole, okay, without the E. For a quantity of a substance, whether we're talking about molecules, atoms, ions, it's an arbitrary unit, just like a dozen, which is equal to the number of atoms in a 12 thousandths of a kilogram of carbon. They use carbon because it is one of the most common, abundant isotopes found in nature, so it was easier to measure carbon versus any other elements. And so this is actually going to be the standard that's used to give us the number for Avogadro's constant, which is 6.02 times 10 to the 23rd. And I use this little kind of half arrow here to express the exponent on the 10 there, 10 to the 23rd. All right, so introduction. Before we can even begin to understand what this unit is about, we need to be able to find the mass of different compounds. So what I want you to do is open your periodic table so we can get started. First, what are the units we use for the mass of atoms? That would be atomic mass units, or AMU. We have looked at this several times. We are in Unit 5 now, so we do see AMU a lot. This unit is located on your reference table as well. And let's look up the mass of one atom of oxygen. In AMUs, okay, this would be 15.9994. Question is, why don't we use grams as the units for massing atoms, just like anything else in nature? Well, this is the reason. Atoms are too small. The number would be very, very bulky, meaning lots of zeros because it's such a small amount. So, for example, if we used grams to mass atoms, the mass of oxygen would be this crazy bulky number here, okay? Or we can convert it to scientific notation, 2.7 times 10 to the negative 23rd. Okay, so this number is telling me that there are 22 zeros in front of that 2. Okay, and I'm not about to say all of those. Right, so here I just looked up the mass of carbon, 12.0107, and this is a little periodic table that I have on Smart Notebook that I can just click on all of these and check their atomic masses really quick, because no one is perfect and we still have to look up atomic masses when necessary. Okay? So what I want you to do is find the mass of these atoms below in your notes. So you're going to use your periodic table and you're going to simply look up all of these elements and put their masses in AMUs. And I'll give you a second, well, actually a few minutes to do that. You should pause the video now to give yourself enough time to look up these masses on your periodic table. Okay, so now that you've had time to look these up, let's double check our answers. Magnesium, the mass is 24.305 AMUs, okay, keep that in mind. Chlorine, 35.453 AMUs, remember, not grams. Calcium, 40.08. Lithium, 6.941. Aluminum, 26.98154. We're using all of the digits. They are significant. And hydrogen is 1.00794. Now, let's go to the next page and say to ourselves, or we're going to fill in here, monatomic or monoatomic elements. One atom of an element that's stable enough to stand on its own. They are considered very rare, not bonded to anything. So I bet you can take a guess what elements these are. Okay, they don't bond to anything. They are stable to stand on their own, meaning they have stable octets. So these things, monatomic elements, are going to be your noble gases. Okay, and then you have diatomic elements. Diatomic elements, or diatoms, which are the elements whose atoms always travel in pairs. So that would be Brinkelhoff, and then also astatine here, which is an exception, bonded to another atom of the same element. So remember, Brinkelhoff to help you. Diatomic elements. So what would the mass be of one molecule of oxygen? Remember, molecule meaning that we're dealing with covalent bonds within other nonmetals, and if we're saying a molecule of oxygen, that would have to be diatomic, as in Brinkelhoff. O2 would be the chemical formula. So here we have O2. The subscript tells you the total number of atoms in the compound or the molecule. All right, so this is a molecule, not a compound. And then, so this will mean that the mass of O2 is going to be 2 times 15.9994 AMUs. And if we take out our calculators and do this, we have 15.9994. Sorry guys, I'm doing this as we go. Multiply that by 2, and you will calculate 31.998 AMUs. So how do we calculate the formula mass and gram formula mass of compounds? Well, I just showed you how to look up the masses of atoms, all right, and then we look at the subscript to tell us how many atoms there are in the compound or the formula. And then we need to calculate that out, okay? So the formula mass, let's look at the definition first. Formula mass is the mass of an atom, molecule, or compound in atomic mass units. So the formula mass of hydrogen atom is 1.00794 AMUs. The difference between formula mass and gram formula mass is very easy. And it's just units. Okay, the gram formula mass of 1 mole of an atom, molecule, or compound in grams. Major difference, okay? Formula mass, AMU. Now we see gram formula mass, which means it's the formula mass in grams. So the GFM, okay, gram formula mass is abbreviated GFM, the same thing, of hydrogen is 1.00794 grams. This is the mass of 1 mole of hydrogen. So what is a mole then? All right, here we go. This leads back to our definition from the warm-up. A mole is 6.02 times 10 to the 23rd units of a substance, kind of like a really big dozen. Okay, obviously it's not 12. Really, really big. A dozen is an arbitrary number, so is the mole. 1 mole of carbon is equal to 6.02 times 10 to the 23rd atoms of carbon, which is equal to 12.0111 grams of carbon. Okay, now some periodic tables have different masses, so don't let that throw you off. Your reference table should say this, but if it's been updated, it might be off by a couple of decimal places, but don't worry, okay, because generally you're going to have the same answer in the end when we use our calculations. So let's practice, and we have to show all of our work when we're doing this. So what is the formula mass? Remember, this is formula mass has to be in AMUs. So that's going to be our final unit. So we have to look up the mass of potassium, which is 39.0983, okay, AMUs. Now, you might have a different value on your periodic table. Again, use the one that you have. I'm using the periodic table that I have with me at home. Carbon has a atomic mass of 12.0107 according to mine, but again, before in the previous example it was 12.0111. And then also we have to look up the next element, oxygen, which is 15.9994 AMUs. Okay, so these are the masses of each element in the compound. But we see subscripts, so now we have to bring that in. So potassium, there's 2, so we have to multiply this by 2. Carbon, we only have 1, so we'll keep that as 1, multiply it by 1, and then we have 3 oxygens. So this mass has to be multiplied by 3. So take a minute, use your calculators, calculate these, and then what you're going to do in the end is add them all up, and that would be in AMUs. Okay, so when you calculate this, you should have something somewhere around 138.2055 AMUs. So that's for the formula mass. Now, the second example is what is the gram formula mass of copper sulfate pentahydrate. Okay, so pentahydrate, I'm using the prefix penta, which is equal to 5, right? And we have water here. So this is a hydrate, and we're going to learn about this in this unit, okay? So this is where I get the name from, pentahydrate, and that little circle there tells me that it's a hydrate. It's not actually part of the formula, but it's been absorbed. Okay, so it's still going to be considered part of the gram formula mass, so we have to look at all of this. So number 1, or in step 1, we're going to look up the atomic mass of copper, which is 63.546. Okay, and then sulfur, which is 32.066. Oxygen, again, we already have that, 15.9994. And also, what else do we have in here? Water. I'm sorry, hydrogen. Okay, and hydrogen is 1.00794. Now we go back and say how many of these do we have. Now, we have a coefficient here, which means that this whole formula is multiplied by 4, or you can multiply the 5 by the subscripts in that part. So we have to consider every single atom in this formula. So let's look. Copper, there's only 1, so we'll multiply that by 1. Sulfur, we have 1, so we will multiply that by 1. Now oxygen, we have 4 here, right? And then we have 5 over here, because the subscript technically is a 1. So 5 times 1 is 5. So we're going to have 5 plus 4 is equal to 9. So we have 9 oxygens in the formula. And then hydrogens, we have 5 times 2, which is going to equal 10. Now, again, if I'm going too fast, please rewind the video and go back to see or listen to how I obtained the number of atoms of each element in the formula. Okay, so take a minute, do the calculations, and we'll reconvene in a second. Okay, so your final answer should be somewhere around this, depending on which periodic table you're using, 249.686 grams. So I'm going to reiterate this again. Gram formula mass, the unit is grams. Watch the unit. All right, so what I want you to do is do some practice on your own. Do numbers 1 through 3 on page 2 in your homework packet. Be ready to answer these in class for a warm-up, and also jot down any questions that you have regarding this lesson. Moles are a difficult concept, so I'd like for you to have some questions ready for class.